Hello, my name's Tim and welcome to my video on creating a basic OpenGL program. I'll be using a beta version of Fedora 18 for this and compiling everything with GCC and linking in a library called glfw. Those are the only two dependencies, OpenGL and glfw, and that's just used for creating the actual window and doing a little basic input. So I recently started creating my own 3D game engine called Portable Glue, and you can find it at portableglue.com. And in that process I had to learn everything from scratch because I didn't really go into this knowing a whole lot about OpenGL. And what I found was that there was a lot of tutorials online that referenced OpenGL 1.1 stuff with fixed pipelines that were no longer really relevant or very useful trying to figure out how a modern shader-based pipeline works. And when I looked to books that were well recommended, most of them also had their own CDs with their own libraries on it, and all the stuff had all of their own cruft in it. So when I wanted to see what a very basic sample would look like, I couldn't really find much out there that did that. So that's going to be this tutorial. I'm going to create a very basic program that will draw a triangle, a red triangle on the screen, and when you hit escape the window will close. This won't be a whole tutorial on OpenGL. It's meant as an adjunct so that you can see what goes on here, and I'm trying something new by explaining it by video instead of just having a blog post on this. And that way it's a little bit more interactive, so when I describe things you can just follow along and research topics further so that you can understand in greater depth. And again, this is just an adjunct and supposed to be pretty basic. So there's going to be 4 listings. We'll include a link to a bzip file that will have all 4 listings. 4 listings of C code and CC, and make shell scripts that will call GCC with the correct options. All this is going to do is tell it to output a main-01 program, compile one file. I have an additional link library directory so that it links in my local copy of glfw, and then I tell it what libraries to link with. I'm not using static linking here. These are going to be dynamic linking at runtime. So first listing, you start off with some basic includes. These are going to be your minimums: DL, FW, header, and the header for standard lib for ANSI C. I define a function for cleanup on exit that will call GFLW terminate. So when something goes bad and I need to exit the program, or the program exits normally, it will end up calling GFLW terminate. So if you're full screen, it would resolve any problems with that, kind of clear up any weirdness that might happen. And it's always good to be clean about things. This is the main function. There's no command line arguments being needed here. So I set up some constants for the window size. I set up a color that I'm going to want, which will be black, so this will be the value that I use. And I set up a flag to control the run length of the render loop. So when this gets set to 0, the loop's going to exit out. Right here I call @exit so that anytime an exit is called or the program finishes, cleanup on exit will get called, which is what I described above. So the next line is to initialize glflw. This has to be done first before anything else in glfl or glfw. That has to be called first, and if that fails we exit. Then we create a window with a width and the height mentioned above and the rest of basic options. And then we create a viewport, which is also width and height. This probably isn't going to matter. The coordinate space for the window we're going to use is basically -1 to 1 in all axes, the default coordinate space. And then this will be our render loop, a simple infinite while loop controlled by this flag that will get set to 0. So I guess it's not infinite after all, but it'll get set to 0 here based off of whether or not the glfw detects that the escape key was pressed, or if the window is closed. If that happens, then running is set to 0, the loop exits, the program returns, and it finishes. At the start of the render loop, it's going to set the clear color, which is what I mentioned before, so 0, 0, 0 with an alpha of 1, so it's going to be a fully 100% alpha black. And then it's going to clear the color buffer and the depth buffer, so 0 everything out essentially. Eventually we're going to put drawing here, but right now we don't have anything. And then we call GL FW swap buffers to switch the display buffers so that everything that we did up in this section will get shown. Right now there isn't anything. And that is listing 1. So if we go through, you can see that I just have these 2 files. This is what the shell script looks like. Compile. And that's the size of the executable with debug info and dynamically linking in GL and GLFLW. We're going to run it, and you see it creates this window. Hit escape, and it goes away. Just what we wanted. So moving on to listing 2. Listing 2 is going to include the use of shaders. This is what we're doing all this work for, is this really cool shader pipeline that modern OpenGL uses, fully programmable. You can program your own effects in it and do a whole lot of stuff. So in order to get things going with that, we have to set a new define before we include the GL headers, because if we don't do this define, you're going to find undeclared identifiers for all the more modern GL function calls like GL get shader. So we set that define, we include the new headers. And then we set up our shaders themselves as string constants in the programs. This is just makes it a little bit easier. You could have them as files, but then you'd have to write in code to read them from the file, and just might as well make things easy while you're learning. Just include them in as string constants. This is about as basic as they get. We're going to use 2 different types of shaders, a vertex shader and a fragment shader. Vertex ultimately controls the position of each vertex getting rendered, and the fragment shader is the color output, essentially. It gets called multiple times potentially per vertex, because if you have a triangle, let's say, that takes up half the screen, there's going to be more pixels that get rendered than vertices, and there's an interpolation that gets done there, and this fragment shader gets called a lot. So this one is going to be an OpenGL 2.0 shader, and this version 1.2 essentially is what that version indicates. That's the GLSL version number for OpenGL 2.0. Does a straight copy of the vertex location to GL position, and the fragment shader just copies 100% alpha value of red, because this is RGB, into the output frag color. So there's not going to be any detail shading, no texture mapping, nothing of that nature, just straight out outputting red for each pixel. So we still got our cleanup function, and we have 2 new functions. Print shader log will call GL get shader, and if you're not familiar with the OpenGL API, often there are multiple versions of function calls that will have different suffixes. So this one, IV, indicates that it does take an integer value for its parameter as a pointer, this one. So there are other versions where, especially when you're buffering data, or not, excuse me, not when you're buffering data, but there are other functions that will have different ones for floats and whatnot. So get shader, it wants to get a value about that shader, and so we pass it a parameter, GL info log length. Info log length is the length of the info log. So if something's gone wrong, that will be non-zero. So we'll go ahead and allocate a new string to hold that length of a string, and then we get the info log using this function, GL get shader info log. We pass it the ID of the shader that we want. I'll explain that in a moment. We then pass the log length that we want to retrieve and the buffer to put it into. We then print it out and free it. This is used to debug any problems that we get when we load our shaders. Shaders get loaded in this function that we created for listing 2. You pass in a GL enumeration, which will be GL vertex shader or GL fragment shader, which indicates what type of shader this is going to be. You also pass in the code, which is mentioned above, so a constant character string, and then this is going to receive the ID of the shader that OpenGL creates. So right here, this is how we allocate a shader in OpenGL. GL create shader. You pass in that enumeration value, so a GL vertex shader, for example, and it'll create a vertex shader, and it'll return you the ID number of that shader. So that's an ID of the object that exists on the OpenGL side of the API. And you manage everything that way by passing around the ID value. So to set the shader source code, you then pass that ID value and tell it how many strings that we're going to pass, which is going to be 1. And since we pass null here, it's going to be a null terminated string. And then this is the string of shader code that we're going to pass in. The next line will compile it. GL compile shader. You pass it in the ID of the shader you want to compile. Pretty simple. So in order to detect whether or not there's any problems, you call GL get shader again, which will get information about this shader with that ID as we got before. And this time, instead of info log length, we want to check compile status. And if compile status is not true, then we have a problem compiling it. So we print that, we found a problem, and then we call the print shader log function that we described earlier to get the info log and write out all the problems. Very useful for debugging shaders, in case you forget your semicolon or somehow blow up an attribute name. If there's a problem, we delete the shader and set the ID value to 0, and things will not draw correctly. In this basic example, doesn't have the best example of error handling, just keeping things nice and slim. I trust that to do a production version, you're going to want to do a little bit more error checking. Now we're going to get back into our main loop. We add a few more variables for the shader IDs and another variable to check the link or status of those shaders. I'll explain that in a moment. We keep our cleanup function the same. We still create our window. We still create our viewport. And then we load our shaders here. This references the function above, load shader. And we tell it to load both the vertex shader and the fragment shader with the source code constants mentioned above. And this is how we get our shader IDs. When that's done, we go ahead and print them out just for kicks. Just shows that something did happen. A little bit useful for debugging, probably not of much practical value. And then right after that, we go ahead and create a shader program. This is what actually is useful in OpenGL, is the program itself. These shaders are just an intermediate step. So we go ahead and create the shader by calling GL create program. We then attach the shaders with GL attach shader. We pass the shader program ID that we just created above, and then we pass in the vertex and the fragment shader IDs. So we attach those two shaders, and then we link them together with GL link program. And just like compiling shaders, we want to make sure things link correctly, so we check the link status by passing in GL link status to GL get program instead of get shader, get program. So we go ahead and check the link status, and if there's a problem, we let the user know, and then we go ahead and print the info log and then exit. So if it makes it past that, things have compiled successfully, so we let the user know. And that will be it for listing 2. The render loop is going to stay the same. So listing 2, we got our make script, basically the same. Compile stuff, slightly bigger executable, dynamically linked still. And you can see that we still have just our blank window, but we also over here have IDs that we outputted, and we say that shader is successfully linked. So that means all of our new shader code worked exactly as we had planned. Hit escape, program terminates, back to command line. So we're going to go to listing 3 now. Listing 3 is where we're going to draw this triangle. We're going to draw a basic version of this triangle by sending vertice data to a built-in shader variable called GLVertex. Listing 4 is going to show you a better way of passing in parameters, but for now we're just going to use this as the first example. So the shaders have all stayed the same. The loading, the printing of the log, that's all stayed the same. We set up our cleanup, we set up the window, the viewport, we load our shaders, we attach the shaders, we link the program. Here I added in calls to delete shader. What this shows is that you can delete the GL shader objects right here for the vertex shader and the fragment shader because they're no longer needed. They're linked into the program, and the program is what we want. We don't care about these shaders anymore, so they can get freed up. Next, we create some data for the triangle. The triangle is going to consist of 3 vertices, naturally, and each vertice is going to have 3 floats for data. So you can see that this triangle is created on the XY plane because only XY values change. Z is going to stay the same. And on a default coordinate system, that means this triangle is going to face us. On a side note, you will also note that the vertices wind in a counterclockwise fashion. That little tidbit of information is handy because the default face value, although I don't have face calling turned on explicitly, the way that normal face calling is that you have to create your vertices in a counterclockwise fashion for the face to be facing you. So this one starts off in the lower left, and then the next one is in lower right, and then the next one is the top middle. So you see bottom, right, middle. And that will go in a counterclockwise fashion. So that means that face is declared that way, so it'll see the default camera. Just one of those things you might want to be on the lookout for in case you're having problems with seeing all your triangles. Check your face calling, maybe disable face calling or switch the default rotation for that and see if that clears up your problem. Either way, we're just declaring 9 float values for 3 vertices. And then we're going to create an unsigned integer to hold the ID for the VBO. This is a buffered object that is going to exist in OpenGL that will contain this data so that OpenGL can then manage it. It can decide when to send it across the data bus and when not to. So what we do is we call GL enable client state, GL vertex array, and then we create that VBO by calling GL gen buffers. And you can pass in a number to indicate how many buffers you want to create. We're just going to create one. We pass it the address of that integer, unsigned integer, so that'll receive the ID as an output. We then call GL bind buffer, and then with the GL enumeration of GL array buffer, so we bind the GL array buffer to the new VBO we just created. So then functions that operate on GL array buffer will then use that VBO that we just created. So GL buffer data is when we actually send the data across. We send it across to the target, which is GL array buffer. We pass in the size in bytes of the amount of data we're going to pass to the size of GL float, since that's the data type for the vertices, and 9. There's 9 floats. So we're not passing in how many vertices, we're passing in not even how many floats, but we're passing in the number of bytes. So make sure you get that one correct. This points to the data array, which will be a void pointer actually. So and for us, it's a pointer to our float array. And then this is the usage declaration enumeration. So there's multiple specifiers you can have here. This one is GL static draw. You can have stream, static, or dynamic, and it can be draw, read, or copy. All those have different usages. You can read up on that further in reference books. Static draw basically means that you don't expect any of this data to change. So it's a hint to OpenGL on how to manage that memory. GL vertex pointer will then set that shader variable GL underscore vertex to use the data that we have here. So that first parameter is the size. It specifies the number of coordinates per vertex. So 3, since we are passing in 3. What type they are, the stride between them in the array. And right now we have what we call a tightly packed array. They're all vertice data. There's no interleave data, like say for example normals or UV coordinates. There's none of that. It's just straight up verts. So there's no need to skip normal or UV data. You just go right to the next vertex. So after that, after we pass in the buffer and we assign the vertex pointer to it, we then go ahead and unbind the buffer by calling GL bind buffer, oddly enough, but passing in a value of 0. This resets the GL array buffer so that further calls on GL buffer or buffer data don't accidentally overwrite something that you did. Or in case of the driver, if you have static draw and you buffer data, you don't want to potentially crash your program because the driver misbehaves when you try to edit data that's already been buffered. So our draw loop, this has changed a little bit. We add in a use program, GL use program, that will use our shader program. That's how we tell OpenGL to do the actual shading and the vertex manipulation. We do GL bind buffer like we did before. We bind the GL array buffer to our VBO for the triangle vertices. And then we just call GL draw arrays. Draw arrays takes in what kind of mode. So there's various things that you can draw. We can draw triangles, but you can also draw points. You can draw things as a triangle strip, as line strips, a lot of different things that you can do with that. We're just going to draw triangles, and this is the first index and the count. So we're just going to retrieve 3 indices for 3 vertices and draw a triangle. And after the draw call is done, and this is what everybody refers to as a draw call, since there are multiple ones. You have things like draw elements and draw arrays instanced, which doesn't exist on OpenGL ES, but there are different versions that behave differently. GL draw elements will take an additional VBO for an element array so that you can specify more precisely what vertices make up a face, which is really handy when you start importing models that are huge. So that's a draw call, and then we unbind the buffer. And the rest of that is the same. We swap the buffer so we show our progress, so we see if we need to quit. Then down here we just tidy up. We delete the shader program and we delete the buffer that we made. So let's go through, and you'll see that the make file is still basically the same, just change the number, compile things, and a little tiny bit bigger, dynamically linked. Here's our triangle, and you can see that since we're making vertices with coordinates of 0.5, you can see that essentially the coordinate space is -1 to 1. So we got it. That's drawing. That's probably drawing a lot of frames a second right now. As an exercise to the user, you can put in an FPS counter to your console. So we hit escape to close that down and move on to the final listing. Listing 4 is mostly the same as listing 3, but instead of having GL vertex like we do up here, we're going to declare our own attribute called invert pos for in vertex position. And attributes are values that are specified per vertex in the vertex shader. There's also something called uniforms, and this is all very basic GLSL stuff. You'll definitely need to know this in order to be of any use in OpenGL 2.0 plus. But uniforms are passed in like per draw call. It's not passed in per vertex, whereas attributes are. So per vertex, the vertex position changes. Things that will be in uniforms are like light positions, model view projection matrices, stuff like this. So we have our own new vector 4, so length of 4 for our vertex position, which is a little bit interesting because we're only passing in 3 floats for vertices, and that's fine. We're not going to use the 4th value, and it just fills in a default value for that, and it's fine. We don't care about that. And we just do a straight up copy. We copy in the position to the in vertex position to the GL position, which is a special value that you need to assign. You have to assign it in your vertex shader. So that's it. That's a small change, but what this will show is how you can add your own attributes, and down below you'll see the code to actually link up with this. The fragment shader has stayed the same. Cleanup, print shader log, load shader, all the same. Our initial parts here of setting up our cleanup, creating the window, viewport, loading the shader, all of that's the same. Right here we have a minor change. We create our program, and then we attach our shaders, but before we link it, critical, we have to do this beforehand. We call GL bind attribute location, and what we do is we pass it the shader program ID, and we pass it a string of the attribute name, so in vertex position, and we're binding it to an integer right here. So we're binding it to an index of 1, which means that from now on, when this links, I can reference this attribute with the integer 1. So when we pass in all the data for that stuff, This is very handy, and this has to be done before linking. This way we won't have to query the shader at each frame, for example, to see where that location is. We just automatically force it right to that one. Really handy. And again, we delete the shaders when we're done with it because the shader program doesn't need them anymore. All of this has stayed the same, the declaration, but this is different. We still enable our client state, we still generate the buffer, we still bind the buffer, and we still even buffer the data, which of course is size in bytes, important. But there's no GL vertex call here, no GL vertex pointer. We don't need that anymore because we're not using that. So after buffering the data, we just unbind that buffer by passing in 0 to GL bind buffer. And then our render loop has changed slightly. Going back to listing 3, you can see that we call bind buffer and then we call draw arrays. In this one, we call bind buffer, and then we have to enable vertex attribute arrays for that index of attribute. So that way that attribute will actually be enabled in the rendering of these triangles. And then we pass in, for that index, we tell it that to use the actively bound buffer. So that's what this GL bind buffer calls. It binds this VBO, tells it we're going to use the attribute, and that attribute is going to point back to this VBO. And we identify that attribute again by using that integer that we forced above. And bind vertex attribute pointer takes in a few parameters. That first one is the index, like I mentioned. This one, the next one, the 3, is the size, the number of components for that attribute. We're going to pass in 3 floats, which is the next parameter. GL false indicates that we do not want it normalized. It wouldn't really matter for our triangle, but normalized means to force things down into a range of 0.1 or 0 to 1, excuse me. And then stride is how we described before. This is a tightly packed vertex array, so we don't need to skip anything. So we just there's stride of 0. And a pointer of 0 means that it's going to be bound to that GL array buffer target. There is a way that you could basically reference client data, client side, instead of having a VBO, but I think you can see here that the amount of code to support VBOs, should the feature be present on the computer that you're running this on, the code that to make VBOs work is pretty small, so really worth it. And then we call GL draw arrays again and unbind the buffer. So those were the only changes for listing 4. We got our make script, make our executable, and run it. Same triangle, same as before. Just this time the shading uses a custom attribute, and so you can see how you bind your own attribute values. And so you can take it from there. There's a lot. Basically, this will give you a known good state of a very small program that will work, doesn't have a lot of dependencies or crazy command line options to compile this thing. It's all very simple. So you can get this going and build up from there. So I hope you found this useful, and thanks for watching.